everyone, welcome back to the Internet Report, where we uncover what's working and what's breaking on the internet, and why. This week, we're looking back at the notable outages from 2025 and analysing the themes that emerged, giving ITOps teams lessons they can take into 2026. I'm Barry Collins, and I'll be hosting today with the amazing Mike Hicks, Principal Solutions Analyst at Cisco ThousandEyes. As always, we included chapters in the episode description below, so you can skip ahead to the sections that are most interesting to you. And if you haven't already, we'd love you to take a moment to give us a follow over at Spotify, Apple Podcasts, or wherever you like to listen. When centralized services fail, they often cause a cascading effect of knock-on outages for other services. We saw this happen on multiple occasions in 2025, didn't we, Mike?
We did. So we had the AWS one, which is a DynamoDB outage, which happened on October the 20th. Now, this started as a DNS issue or manifested as DNS issue, and it was affecting the DynamoDB, specifically in US East 1. But then that cascaded through the EC2 instances and some load balancers, but it actually hit some sort of third-party services who are actually utilizing this in the back end. So it hit the likes of Slack and Atlassian, and this disruption lasted around sort of 15 hours. This was essentially a regional failure, but it had global impact because it was impacting the control plane. So services like the identification access management and some global tables, which are architecturally tied to that specific region. Now, a similar thing happened to Google Cloud on June the 12th. This was essentially identification access management failure, but this was then impacting these third-party services themselves. So the ones that actually use this for the authentication process to access the services in the back end, not to log on to the system. So the likes of Spotify, Fitbit, and some Cloudflare Worker KV and some other Cloudflare services were sort of impacted. This three-tier cascade effect. Now, the key pattern with these centralized services are that they have a wide blast radius. So when they fail, lots of things fail. Now, these dependency chains are traceable in as much as you can map out what depends on what and after the fact. So we can see what was impacted by what was impacted by that. So they're sort of singular with essentially a clear failure point, not scattered across multiple systems, which is this cascading effect we actually see. But the traceable doesn't actually mean you can stop it happening. Once a cascade starts, like a domino chain, you start to see them falling over and dependent services start to go down on those. Regional failures can actually spread globally through the control plane dependency. So multi-region doesn't necessarily protect you if we're actually having the control plane that's sort of centralized. Now, the real problem with these are these third-party dependencies. They're not always obvious. So we call these hidden dependencies or these nested dependencies. They're not obvious until they actually bite you. So if say a Slack user, you may not be aware that you depended on a DynamoDB, or as a Cloudflare using a particular Cloudflare service that you actually weren't then dependent on the identification access management system. So if those actually go down, you have this cascading effect that sort of takes down your services.
Two Azure outages in October revealed an important nuance about distributed systems. Explain what you found.
So these are both Azure front door issues, or they manifested Azure front door issues. The one on October the 9th was sort of regionally containment. So we can say sort of working as designed. Now, this was an infrastructure failure at the edge. It was specifically in EMEA, it was a Europe, Middle East, and Africa, so that region there. In this case, a software defect caused the edge sites themselves to actually crash. And then the remaining sites that were left, the redundant ones there, got overloaded. So we started to see this degradation in terms of services specifically for that region. The other regions weren't impacted. So the Americas and other regions carried on working fine. The impact was to those users accessing through those EMEA edge locations. Now, on October 29th, we still had the Azure front door. In this case, it was actually a configuration change that actually caused the issue. This then manifested itself as HTTP 503 errors, some timeouts, some connection cancellations. But because this is a configuration side, this was actually globally. So all regions failed simultaneously despite this sort of physical infrastructure separation. What this nuance then reveals is that infrastructure failures, so hardware, software, capacity, compute, often stay contained within sort of regional boundaries. These systems are sort of designed for resilience and isolation themselves. Now, where you have a configuration change, you need to apply that across all regions simultaneously, depending on what you're changing from a configuration perspective. Configuration then is a global dependency, even in that distributed architecture. So you can have sort of perfect regional isolation for the infrastructure, but one config change can actually take everything down. So this means that distributed and resilience aren't necessarily the same thing. You're distributed for infrastructure failures, but centralized for configuration. Operationally, what that means is you need different response playbooks. A regional issue, you can effectively route around, you have a workaround. a configuration issue, you can't necessarily work around there. The architecture itself doesn't protect you from all these failure modes equally.
We've established infrastructure failures are normally regional, but can have a global impact. Let's dive into that more deeply and explore scenarios where that happened in 2025.
So let's go back to the AWS DynamoDB outage on October the 20th that impacted, as we said, US East 1. This started as a pure regional failure. This DNS race condition in US East 1 only. That specific region's DynamoDB endpoints became unavailable. But here's where it went global. So the AWS's Identification and Access Management Service and DynamoDB's global tables were architecturally dependent on US East 1 as their control plane. When we talk about control plane, what we're actually talking about is this centralized system that handles the coordination, authentication, and configuration, effectively the decision-making layer. The data plane handles the actual requests and traffic, the doing work layer, as you will. So the control planes get centralized because you need a single source of truth. You can't have conflicting decisions about who's authenticated and what the current configuration is. Now, for example, if you were to revoke someone's access, you'd need that decision to be immediate and consistent everywhere. If each region decides independently, you're going to get these conflicting answers. So why does this then create a global impact? So if US East 1 goes down, but your application is running in EU West 1, it doesn't really matter because you still need to talk to the control plane in US East 1. So services like Slack, Atlassian, Snapchat were in multiple regions all failed because they couldn't reach this centralized control plane. The regional infrastructure itself was fine, but without this control plane, nothing can actually make decisions. There's a trade-off to be had here. So centralized control planes create this single aggregation point where if they go down, everything can actually stop. But distributed control planes create what's called a split brain scenario. So different regions can make conflicted decisions. So, for example, region A thinks that user is authenticated. Region B thinks they're not. Which is right? How do you actually resolve that? Or worse, you revoke access in one region for security reasons, but another region hasn't seen that change yet, hasn't propagated, and still grants access to that thing. Now, operationally, an outage is clear. Service is down, fix it. Consistency issues are subtle. Some requests work, some don't. Different users see different states. Now, that's actually harder to detect, harder to debug, and can cause security or data corruption issues. So the centralized model accepts the availability risks to avoid that consistency nightmare.
We've talked many times on the Internet Report in 2025 about the different nature of failures, how some are sudden lights on, lights off outages, and others are more intermittent. Explain how different types of architecture can affect the nature of such outages.
So let's think about centralized services. These are effectively binary failures. There's a lights on, lights off. So, things like AWS DynamoDB, Google Identification Access Management Systems, when they fail, they're completely down. You get clear symptoms. Everything stops working at once. Operationally, these are straightforward. The service is down. Users can't do X. And the status page can say definitively we're experiencing an outage. A distributed edge system with staggered updates will have intermittent failures. So if we look at the Cloudflare outage of November the 18th, this was a bot management configuration file. It actually exceeded a hardcode limit and actually caused the proxy software to crash. But here's the key. The proxies refreshed their configuration on a staggered 5-minute cycle. At any moment, some proxies successfully loaded. They had smaller config files and they're actually working fine. Other proxies tried loading the oversized file and crashed. This creates a fluctuating availability. Some requests to service appear to succeed and then fails minutes later and then succeeds again. So staggered updates are intentionally designed. You don't want all edge nodes updating simultaneously because we have this situation where we're loading in. If the update is actually bad, everything goes down at once. But when a bad config gets deployed, it can create this rolling failure pattern. So each proxy independently decides to refresh on its own cycle. So you never have 100% failure, but you also never have 100% success during the incident. And this global impact can happen, but it's intermittent rather than this binary. Now, for an operational implications of that, intermittent failure is actually hard to diagnose because you get this situation where it works for me versus it's broken for me. Both could be true at the same time. And status updates are difficult. The service vendor can't actually say the service is down because it's working for some users. Monitoring can show partial failure, but which user affected keeps changing. And recovery can also be intermittent. As a fix deploys, services recover progressively. As each proxy loads the corrected config on each of its refresh cycles. So it's actually much harder to communicate to the users than a clean outage. So when we see this degradation pattern, it's a little bit harder to understand what's going on and actually pinpoint where that exact issue is.
It's become something of a cliche that when a major outage occurs, DNS is the culprit. But we did see multiple DNS-related outages in 2025, albeit with completely different failure mechanisms. Remind us what happened with Zoom and Cloudflare, Mike.
Yeah, I think what you said, sort of DNS related, that's the key here. So the Zoom one on April the 16th, we had this top level domain that is the sort of the .us part of zoom.us or the .com in example.com was actually missing. The missing name server records at this top level domain tell the internet, where do I find this information about zoom.us? Think of it like a phone book where the top line domain servers are the main directory that says for zoom.us, ask these specific name servers. Now, Zoom's authoritative name servers, which is on AWS Route 53, were actually fine. They were correctly configured and they're actually sort of working. So if you query them directly, they were going to return the right records. But the problem was the top level domain name servers didn't have the name server records pointing to Route 53. So the DNS clients had no way to know where they actually had to look for zoom.us records. The phone book was effectively missing the Zoom's entry. All Zoom servers were inaccessible for around sort of 2 hours. And this actually included the status page itself. So you can actually identify what was going on. Now, if we then look at the Cloudflare one, which is on July the 14th, this was actually a BGP routing issue. BGP route withdrawals took Cloudflare's DNS off the internet. So this was a configuration error introduced weeks earlier. It was dormant until an unrelated change triggered it. Cloudflare's route announcement disappeared from the global routing tables. So there was no network path for DNS queries to actually reach the 1.1.1.1, their public resolver. And this was actually down for about an hour. So anyone using Cloudflare's DNS couldn't actually reach websites and applications. So why do these differences actually matter? So we're talking about different layers of the stack. Zoom, the DNS itself was working, but the delegation chain was actually broken. The pointer was missing. Now in Cloudflare, it was network routing problems. The DNS infrastructure was fine, but it's actually unreachable. So there's different recovery paths we actually have there. For looking at the domain record, the issue requires coordination with the domain registrar. You can't actually fix yourself. You need third-party involvement. With the BGP routing, it's a network-level configuration. You control it, but you need to identify the fix and the config error to either route around to re-advertise your network itself. So these had different diagnostic signatures. So they both manifested DNS issues. Whereas Zoom was direct queries to name servers work, but normal DNS resolution failed. We're going to point to a delegation problem. In Cloudflare's situation, we can't reach the DNS service at all. The network was unreachable. So it's not DNS misconfiguration. The broader point to all of this is a DNS problem is sort of very vague. It tells you almost nothing about what's actually going on. You need to actually understand sort of which layer failed, the delegation change, the authoritative servers, or network reachability, as each requires a completely different troubleshooting and different parties essentially who are responsible to actually fix it.
Often the cause of a failure isn't obvious. Explain how you're able to combine signals to diagnose the cause of outages in 2025.
So the problem if you look at single signals is that individual symptoms can mislead you. The network looks fine, but users can't complete tasks. So where's the problem? Services return errors. Is it the network edge or is it the back end itself? What you need is combination of signals to reveal where the failure actually is. So actually look at Slack, which was an outage occurred on February the 26th. The network connectivity in this case was completely intact. We saw no coinciding network conditions, no significant latency, no significant packet loss, and parts of Slack's infrastructure globally appeared healthy. And the load balancers appeared to be responding normally as well. Authentication was working fine. Users could actually log in. They could browse channels. But what the issue was, the messages wouldn't send. And was actually, when you went to send a message, it was actually returning an HTTP 500 errors. Now, by looking at this combination, it actually sort of revealed the location. In this case, the database routing layer. The network was working, plus the authentication was working, plus the message was failing, equals this specific layer between the web app and the database itself. If you actually look just at the network metrics, you'd have seen the healthy path, would have misdirected you to the investigation. If you only saw HTTP 500 errors, you might have assumed a general backend failure itself. So if we then look at the Spotify April 16th one, we had an HTTP 504 gateway timeout and a 502 bad gateway errors. But connectivity to the front end was normal. DNS resolution appeared to be working. There was static content loading from the CDN itself. Now, again, this combination of server-side errors plus an intact network plus successful static delivery equaled a back-end service issue. Specifically, video playback services, so streaming manifest generation or authorized playback URLs. So users could access a platform interface, but videos wouldn't play. If we're thinking about it from the pattern, what do we actually look for? So we need to have these combination of signals. So the network health, if we look at the latency, the packet loss, and the routing, the connection establishment, the DNS resolution, the application behavior, any HTTP status codes, which functions work versus which fail, and the timing patterns. Do we see simultaneous across regions, intermittent, or progressive? Now, why does this matter operationally? It's no single signal provides sufficient information. You need to be looking and monitoring across multiple layers, the infrastructure and the application behavior and the user capability. So during incidents, what you need to do is to stop this knee-jerk reaction by looking at one individual signal. What you need to do is look at combinations, because this is going to tell you about where in the architecture problem resides. And the combination actually narrows the search space, which can actually sort of save hours of investigation time and actually arm you in terms of what you can do from a mitigation perspective.
We saw multiple incidents in 2025 where configuration changes led to incidents, sometimes repeated incidents in quick succession. Explain why you think ITOps teams should shift from the mindset of preventing all configuration issues through testing to accept that they can't test every scenario, but are ready to respond quickly when incidents do occur.
We actually look at the evidence that this testing is not going to catch every particular scenario because we have so many different moving parts and different conditions. Even if we're testing in this environment, we can't then understand exactly how it's going to interact with all these different third parties from there. So if you look at the Asana outages, these occurred on February the 5th and February the 6th. The February the 5th one was a configuration change, and it caused an increase in server logs. The logging infrastructure itself then overloaded and causing the servers to restart. And it was, again, this domino effect. We had this cascade failure. What they did in that case, they rolled back the config. What typically happens once you've actually rolled back a configuration or implemented a software patch and then had to roll it back is ultimately they sort of try again. And this is what appeared to happen in this case. So on February the 6th, they tried again, and we were going to assume they actually added additional safeguards. In this case, this sort of crashed some servers with 20 minutes of complete downtime. Rolling back the config triggered a cascading failure in the network routing components. So these weren't deliberate, obviously. These were likely reattempting after initial failure with more precautions in place. Now, what this then shows us is that the distributed systems with these numerous components makes it impractical or almost impossible to test every possible interaction scenario itself. With the Cloudflare one on November the 18th, this was this bot management file. The bot management configuration file which exceeded the hardcode limit. Now what happened in this case was a database query error that caused duplicate rows. This then doubled from around 60 to 200 and above features, which then exceeded this hardcode limit and which then caused the proxies themselves to crash. Now, the sequence itself was we had these database permission changes, we had the duplicate rows, the oversized files, the hits, the limits. The components that actually executed millions of times before this issue and this specific sequence occurred. And there's actually no way that testing could realistically catch this combination. So what these outages sort of share, there were multiple components interacting. There were specific sequences or conditions needed to actually trigger the outage. There are effectively edge cases where the exact combination of conditions is really difficult to anticipate. So these are all built on reasonable designs, meeting unexpected interaction patterns themselves. So we're going to shift from this test everything before deployment to prevent all configuration issues, therefore have zero configuration related incidents, to an environment where we're deploying carefully but responding quickly. So we accept that distributed systems are incredibly complex and too complex to test every possible scenario and interaction that can occur. What we really need to do is minimize that time between the deployment and ultimately the detection, the identification and the rollback itself. So identifying specifically what's going on, which layer within there is happening, who's responsible for it, but more importantly, that a change has actually been made. So a change is made, we actually want to understand what's happening so we can actually sort of roll that back. Because there are instances where if we don't detect it early, it's impossible to roll back. And you have to go through with it and try and do that fix, which leads to an elongated outage time.
Finally, Mike, just summarise your main takeaways from the outages we saw in 2025.
So number one is that know your architecture's failure signature. Different architectures fail in characteristically different ways. Centralized services cascade through dependencies predictably. They have wide blast radiuses. Distributed systems may contain failures regionally, but configuration still impacts instances globally. So if you understand your specific failure pattern, it's going to help you to interpret the symptoms faster when an incident actually happens. So before the incident, you can actually see if you can identify these potential failure modes, Then during the incident, this architecture knowledge helps you focus the investigation appropriately, where we need to look, where we want to go down to. The second point I take is that single symptoms lie. What you need to do is to look at these combinations. The network is healthy, but users are failing. It's a back-end issue. Everything fails simultaneously across different channels. There's a shared dependency. Intermittent failures like staggered rollout or edge systems. What you need to do is to be able to monitor across the layers, understand the network health in context of the connection establishment and the application behavior, as along with all these timing patterns. By understanding these combinations, looking at these signals, you can narrow that search space down and you can actually understand what's going on. The third one is blast radius is actually predictable if you understand the architecture. Infrastructure failures will often stay regional. Configuration changes affect all regions simultaneously, even in a distributed system. And the dependency cascades extends failures beyond those initial points. These third-tier dependencies bite you. Regional doesn't necessarily mean you're going to contain if your control planes are centralized. Understand these patterns informs mitigation planning before the incidents occur. And number 4 is configuration complexity is here to stay. If we look at distributed systems, they're too complex to even contemplate testing every possible permutation you've got there. So we need to shift the mindset from this, prevent all issues through testing, to be able to respond quickly when they do occur. Build these capabilities for rapid identification, identify them early so you can do fast rollback, think about things like stage rollouts, and more importantly, be able to communicate what's going on. If from a user or for your stakeholders' perspective, if they understand that there is an issue and something's happening, they're more likely to sit and wait to understand what's happening as opposed to being fed no information themselves. Ultimately, what you're trying to do is to reduce that time between the detection and the recovery. My final thought on this is that 2025 showed us that the internet infrastructure is incredibly complex. It's also relatively resilient, but there's no single architecture that's actually sort of safe. Each is going to have different failure modes and specific failure modes. And success isn't necessarily about perfect uptime. It's about resilience and business continuity. And to do that, you need to understand your risks and having the appropriate response capabilities themselves. The final thing is that patterns repeat. And if you identify the pattern, knowing them is going to help you to be ready in the future, not just from this planning perspective, but when they do occur, to be able to understand what mitigation or what process you need to put in place.
And that's our show. Please give us a follow and leave us a review on your favourite podcast platform. We really appreciate it. And not only does this help ensure you're in the know when a new episode is published, it also helps us to shape the show for you. You can follow us on LinkedIn or X at ThousandEyes, or send questions and feedback to internetreport@thousandeyes.com. Until next time, goodbye.